Quadrilaterals. As you might remember from our polygon lesson, quadrilaterals are four-sided figures that are enclosed shapes made up only of straight lines. And they come in all sizes and shapes. For example, we have parallelogram. Now, parallelogram, traditionally you would think of just this. Two parallel sides where each pair is at a different angle and a different side length potentially. That is the traditional parallelogram. However, there are several other shapes that fit within the family of parallelograms. For example, a square, a rectangle, and a rhombus. What do each of these have in common? Well, they have two pairs of parallel sides. Thus, they're parallelograms. But more specifically, we know a square has 90-degree interior angles and all the same side lengths. So the sides are all congruent as denoted by the hash marks there. And a rectangle also has pairs of sides that are perpendicular to each other or 90-degree interior angles. And the pairs of sides, much like our traditional parallelogram, are different from each other. We have a length and a width as opposed to four sides of the same size. The rhombus has all four sides the same, just like the square, but like our traditional parallelogram, the pair of sides are parallel to each other, and the other pair, which is not at 90 degrees or perpendicular, is parallel to each other as well. So these are all examples of parallelograms. But that is not the only kind of quadrilateral we have. We also have kites. Everybody likes to fly a kite. The kite essentially has two pairs of sides that are each the same length. So I've got two that are the same length and another that are the same length. And there's no set relationship in that the sides are parallel to each other or not. Likewise, we have a trapezoid. Trapezoids have two sides that are parallel to each other. So I've got a top and I have a bottom that are parallel. And my other two sides are not necessarily parallel. And we can get even crazier into what we would call a complex quadrilateral, in that the sides intersect each other, which looks very different than many of the other quadrilaterals, but indeed it still is a four-sided figure closed and made up of straight lines, so it's a complex quadrilateral. And we have other irregular quadrilaterals like the one shown. This is four sides and they're all straight lines. It's a closed shape, so it is a quadrilateral. However, you can see this vertex seems to go inward, which essentially makes this a concave, not a convex like the others, quadrilateral. So as you can see, they come in many shapes and sizes. However, there's certain things or aspects about quadrilaterals we do know, regardless of any of these shapes, with the possible exception of the complex quadrilateral. All the quadrilaterals' sum of interior angles is 360 degrees. We saw that in an earlier class, where we know the sum of interior angles equals 180 degrees times the number of sides minus 2. So for quadrilaterals, n equals 4, so that's 180 times 4 minus 2, which is 360 degrees. That's the sum of all interior angles. In earlier lessons, we learned how to calculate the areas and the perimeters of many of these shapes. For example, we saw that the parallelogram's area is the vertical height times the length. The square is the side times the side, or s squared. The area of the rectangle is the length times the width. And the area of a rhombus was that vertical height again, times the side length, s in this case. And for the trapezoid, the area was that vertical height, again, times the average of the top, b2, and the average of the length of the bottom, b1. So it's 1/2 b1 plus b2 times h. What happens if we double the lengths of one of the sides? Let's start with the square. If I doubled the side of my square vertically and I doubled the side length horizontally, I would end up with something like the new square, which would actually be of an area 1, 2, 3, 4 times the original area of my square. So let's take a look at that. If my side S becomes 2 times my side S, I double the length of the side, I know my area, which is S squared, becomes 2S squared, which actually works out to 4S squared, which, by the way, is 4 times my original area. Exactly what I expected from the diagram shown above. Let's look at a rectangle. What happens if I increase my length by a constant scale factor, become the new length, that's length times scale factor, and I increase my width by the same scale factor again to become scale factor times width. So suppose we had original length L, and our scale factor becomes 2. We know our length for the expanded rectangle is 2 times L. And our width will be multiplied by the same scale factor. It will be 2 times W. Our original area of that rectangle would have been length times width, but our new area is going to be the new length times the new width. In that case, that's 2 times L times 2 times W, which in turn equals 4L times W. And we know the original area equals L times W, so that is the same as 4 times the original area. So just like the square, when we increase or multiply the length by some scale factor, in this case we doubled it, but of course we could have it or make it a fractional amount. Once we change the lengths by a certain scale factor, it changes the area. New area becomes scale factor squared times the original area, which in this case of a scale factor of 2 times, that was 2 squared, which equals 4 times the original area. If we tripled the lengths of my square or my rectangle, my new area will be the scale factor squared. So the new length is 3 times the old length, my scale factor is 3, and my new area will be 3 squared times the old area, which is to say it equals 9 times my original area. Even if we don't know the exact area or dimensions of the quadrilateral shape, we still know if I multiply all those dimensions by a particular scale factor, my new area will be the scale factor squared times the old area. So question, that works for quadrilaterals. Does it work for other shapes as well? Triangles, circles? The answer is yes, of course. It's the exact same relationship. So let's look at a circle, for example. Suppose we had a scale factor of 2 for the radius. We increase the radius to double its original length. The original area of the circle would have been pi r squared. The new area of the circle will be pi times 2r, our new radius length, quantity squared, which works out to 4 pi r squared. And pi r squared being the original area, we can substitute that back in, and we can see that the new area is 4 times the old area, or again, it's multiplied by the square of the scale factor. How about a triangle? Well, let's take a different scale factor. Let's use 5 in this case. So my base becomes 5 times my original base, and my new height becomes 5 times my original height. And my original area was 1/2 base times height. My new area will be 1/2, now 5 times the base, times 5 times the height, which in turn equals 25 times 1/2 base times height. And I know 1/2 base times height was our original area, so it's essentially 25 times our original area. Our new area is effectively, again, the old area times the scale factor squared. So regardless of the shape, the relationship still holds. A new area will always be the scale factor squared times the old area whenever we scale lengths for any shape, a circle, a triangle, or a quadrilateral, or lo and behold, even if I had this funky blob of a shape, and I doubled the basic dimensions of that funky blob of a shape, I would have something that is 4 times the original area. So I've extended beyond the concept of quadrilaterals, but understanding conversions from lengths to areas, and eventually next lesson we'll see in volumes, is a useful relationship to know.